Well, hi guys. We're going to do some general solutions to trigonometric equations, and specifically in this video just some worked solutions, solid worked solutions to help you to understand how to solve these tricky little beasts. Alright, so let's go. Now, okay, we've got 5 questions for you. We'll just see how we go for time as to whether we get through them all. First one, find the general solution to each of the following equations: a sine, a cos and a tan. Well. So let's go for it. A. Sine of x equals 0.5. Now you'll notice there's no x domain specified, so that means you've got to give them a general solution, right? Now, sine of x equals a half. Now, this is what you do. You first of all think about quadrant 1 and what the basic angle in quadrant 1 would be, which has a sine of a half, and that happens to be pi on 6. Next thing you do is you draw a little quadrant or cast diagram, as I call them, and then you mark your C for cosine being positive, A for all of them being positive, S for sine being positive, T for tan being positive, and then I put a circle around the quadrants which I'm interested in here, which are the 2 quadrants in which sine is positive, because sine of x is positive a half, right? Then I mark in my little angle here. That's a pi on 6 from the horizontal in quadrant 1, and it's pi on 6 from the horizontal in quadrant 2. Okay? Now, when you've done that, it's easy from that point onwards. So therefore, what you say for the general solution is, therefore, x is pi on 6 plus 2k pi, or 5 pi on 6. That's this angle here, from the positive direction of the x-axis around to there, is 5 pi on 6, or just pi on 6 short of pi, okay? And this one here, of course, is just pi on 6. Now, you're wondering, what is the 2k pi? Well, this just means k is any integer. That means k is an element of the integer set of numbers. So you're really saying that k could be positive, or it could be negative, or it could be 0. And you're doing any number of multiples of 2 pi, because that means you could have, for example, pi on 6, or pi on 6 plus 1 revolution of 2 pi if k was 1. Okay, so pi on 6 plus 2 pi, or if k was 2, you'd have pi on 6 plus 4 pi, or if k was 3, pi on 6 plus 6 pi, and so on, so on, so on, and so on, and so on, forever and ever and ever and ever and ever. Amen. And also, you could go backwards. You know, k could be negative 1, so that'd be pi on 6 minus 2 pi, or pi on 6 minus 4 pi, pi on 6 minus 6 pi, and so on and so on. You get the idea, don't you? And of course, the other solution is x is 5 pi on 6 plus any number of revolutions of 2 pi, okay? Yes, that's the idea of it. Now, alternatively, there's this really weird notation for sine, which only works for sine, and it is really ingenious. It goes like this: x is n pi plus minus 1 to the n times the basic angle, okay? And n, in this case, is also an integer. Now, I know that looks really weird, and it's very, very unintuitive, but if you plug some values of n into there, you'll see that it generates exactly the same solutions as this one up here does. Both of them are correct, and it doesn't matter which one you use. Just to illustrate the point down here, say for example if n was 0, then x would be 0. Now minus 1 to the 0 would be 1, and that's just pi on 6. So therefore that solution is just pi on 6, which corresponds to what we got up here in quadrant 1, doesn't it? What about if n was 1? Well, then you'd have x would be pi minus 1 times pi on 6, so it would be pi minus pi on 6, which is 5 pi on 6. You see how ingenious it is? It's absolutely amazing. So that one works for sine, only for sine, okay? So you can have that one up your sleeve if you need it. Right, here comes B. 2 cos 3x equals root 3. Okay, therefore cos of 3x equals root 3 on 2. Now, same old, same old. We go for the basic angle now. Basic angle in quadrant 1 would be pi on 6, because cos of pi on 6 is root 3 on 2. Okay, now we're going to do our cast diagram, as I call them, and then note the quadrants that we're interested in for a positive result here. Cos of 3x is plus root 3 on 2, therefore we're interested in the quadrants in which cos is positive. This one and this one, okay? So now we can come up with our solution. We can say, therefore, 3x, remembering this is a cos of 3x, guys. That's a bit of an extra complication, but don't worry, we'll sort it out. So 3x equals, now, this is the notation we usually use for a positive cos result, like root 3 on 2 plus root 3 on 2 is what I mean. We say that the angle could be plus pi on 6, or it could be minus pi on 6, according to our cast diagram. There's plus pi on 6, there's minus pi on 6, then plus any number of revolutions forwards or backwards, because k is an element of z. And by the way, please don't leave out that k is an element of z, because you'd be wrong if you did. If you're going to go putting extra pronumerals into anything, you have to define what you're doing. Okay, that's really, really important, and students forget that all the time. Now, this is 3x equals plus or minus pi on 6 plus 2k pi. So therefore, we're going to solve it for x now. So you divide right through by 3, and you get x is plus or minus pi on 18 plus 2/3 of k pi, where k is an element of z. And thank you, Mr. Box. That's it, guys. That's the solution to that one. Okay, how are you feeling? So you see they're very, very simple. You just got to get into the groove and into the rhythm of them. Okay, what about C for you and me? Root 3 tan x equals minus. This is a minus one now, so beware. We'll solve it for just tan of x. And what do we get? We get minus 3 over root 3, which is minus root 3. Okay. Now, okay, basic angle time. That would be a pi on 3 angle in quadrant 1, which has a tan of root 3. Okay, but we don't want root 3, we want minus root 3. So we get our cast diagram out and have a look which quadrants tan would be negative in. And there they are. Quadrant 4, yes, and quadrant 2, okay? I'm showing you the displacement of pi on 3 from the horizontal, okay? Now, remembering that tan only has a period of pi, we can express our general solution like this. We can say, therefore, x is, now I chose this angle here, this one in quadrant 2. I said 2 pi on 3, that's what it is from the positive direction of the x-axis. 2 pi on 3 plus k pi. It's only k pi, okay? Any number of cycles of tan, which cycles every pi. It repeats every pi. Its period is pi. Okay? So that's different from sine and cos. You've got to go 2 pi with those. Just 1 pi times k for tan. Now, guys, I could have easily said x was minus pi on 3 plus k pi. I could have done that. So, there's different ways of expressing the same thing. You see, that's what I could have done, and there's another one I could have done too. I could have also said that x is 5 pi on 3, which is another way of saying minus pi on 3. It's the same angle, plus any number of k pi's, okay, where k could be positive, k could be negative, or k could be 0. Are you getting it? Okay, so don't think you've got it wrong if the textbook says something different. You've really just got to plug in values and see whether they agree with what you've written, okay? So please don't give up the ghost that easily. All right, question 2. Find the first 2 positive solutions, okay, to each of the following equations. All right, so we better do the general solution and then start plug and chugging a few values of k in and get the first 2 positive solutions that way, okay? All right, this one, sine of x equals a half. The solutions are x equals pi on 6 plus 2k pi, where k was an integer, or x is 5 pi on 6 plus 2k pi. And now we've got to find the first 2 positive solutions, all right? When k is 0, x is pi on 6 or 5 pi on 6, and they are obviously the first 2 solutions, guys, because that's quadrant 1 and quadrant 2. Yes? Okay, very good. Number B, 2 cos 3x is root 3. Okay, well, from question 1b, we found that the general solution to that was x is plus or minus pi over 18 plus 2/3 k pi, where k is an integer. Okay? Now we've got to find the first 2 positive solutions. So when k is 0, we're just plugging away here to see what happens. Okay? Always start with 0, I think.
It's probably the best one to start with. X would be plus or minus pi over 18, and only one of those is positive. So that'll do us, and that's pretty close to 0, so that's probably got to be the first positive solution, I would think. Now, what else will we try? Well, just try something. Try k as 1 and see what happens, okay? If k was 1, x would be, okay, it would be plus or minus pi on 18 plus, remember it was 2/3 of pi, so that's 12 pi on 18. Now let's see where that takes us, guys. That'll be 11 pi on 18 or 13 pi on 18. Okay, so we can say the first two positive solutions are going to be pi on 18 and 11 pi on 18. Okay, the pi on 18 came from when k was 0 here, and the other one there, the 11 pi on 18, which is just past pi on 2, which would be 9 pi on 18, is this one, which came from when k equals 1. Okay, so we've identified the first two positive solutions by just plugging in k was 0 and k was 1 into the general solution. Yeah? Very good. Okay, what about C for you and me? It's a tan one. We did that in question 1C, so we know that the general solution was x was 2 pi on 3 plus k pi, where k is an integer. Okay, k is an element of z, and capital Z is the set of integers, okay, according to our naming conventions. Now, we've got to find the first two positive solutions. Well, what about if k was 0? That would be 2 pi on 3. What about if k was 1? We'd get 2 pi on 3 plus pi, which would be 5 pi on 3, wouldn't it? Yes. So they're going to be the first two positive solutions, guys. Easy as, yes? Are you starting to feel a bit more confident? I really hope so, because they're really not very hard. It's just the same old routine you do with each of them. So let's, oh, look at this one. This looks a bit hard, doesn't it? Well, fear not. We will just absolutely smash this with our standard systematic procedure. Now, what are we going to do? Find all the solutions for x in the interval minus 2 pi to 2 pi, but not including either. Notice the round brackets. So they're being very crafty here. They're leaving out the end points, but they want everything in between. Well, all right. We better do the general solutions, because that's what we've been asked for, and then we'll identify the solutions within that interval from minus 2 pi to 2 pi, non-inclusive. Now we'll just divide by 2, and then we'll say, therefore, that's equal to root 2, 1 over root 2, I mean, sorry. Therefore, we better do our basic angle now. In quadrant 1, the angle which has a cos of 1 over root 2 is pi on 4. There's our cast diagram, and I've identified the two quadrants which we're interested in to get positive trig ratios for cos. Okay, so pi on 4 up from the horizontal, pi on 4 backwards from the horizontal. So what we can say that therefore, now remember, this is what we're doing the cos of here, guys. Look, cos of 2x plus pi on 4. So we're saying that therefore 2x plus pi on 4 is equal to, okay, either of those two angles, plus or minus pi on 4, plus any number of revolutions. Okay, a revolution is 2 pi, so any number of those would be 2 pi times k, where k is any integer, plus, minus, or even 0. Okay, now what we've got to do now, guys, is we've got to solve this for x. Okay, now be careful, it's just like an equation now, except we've got a little bit of funny business going on here. We've got a plus and we've got a minus, so you've just got to watch our p's and q's while we're solving that. So we're solving for x. We're going to subtract pi on 4 from both sides firstly. So now you just check with me whether you agree with what I got. Okay, do you agree with that? If it was plus pi on 4, then subtracting pi on 4 from both sides would just leave you with the 2k pi. If it was minus pi on 4, subtracting pi on 4 from both sides would get you minus pi on 2. I think we've still got our ducks in a row okay, don't you? Alright, very good. Now we will divide both sides by 2. Woohoo! Divide by 2. And we get that.
Well, that's pretty exciting, and that's the answer. Woo! That's the general solution. Now, of course, we've got to find the solutions which reside within this interval here. Okay? Now, all right, let's go for it now, guys. We can start with k equals 0, then we can go from there. Okay? We can go into the negative values and the positive values of k to capture all the solutions required. We just keep going until we get out of range. That's what we do, guys. Okay, so I'll show you. So when k is 0, we can look at this general solution here. We can say, all right, that would make that a 0, and it would make this minus pi on 4, wouldn't it? Okay, now, are both of those in range? Look at it. They are. So both of those are valid solutions, right? Let's do another value of k now. I'm going for k as minus 1. So that would mean, you have a look, that would be minus pi or minus pi on 4, and k is minus 1, so that would be minus pi on 4 minus pi, which would be minus 5 pi on 4. Now, are both of those valid? They are. They're still within the interval we need, aren't they? So let's keep going. We'll try k as minus 2 now. See how we go. Try our luck, eh? Well, oh my goodness, I think we struck out. Look, this one is right on the end point. It's not allowed because we've got a round bracket here. I mean this one, round bracket there. So that one's out of contention. This one here, okay, 4 into 9 goes 2 and 1 over. So that's minus 2 1/4 pi. So that's out of range, guys. Out of range. They're both out of range, yes? So they're no good. So we'll stop going with the negative k's now. Let's start doing the positive k's. Why don't we go for k equals plus 1 and see what we get. Okay, using this formula, we'll get 1 pi there, and we'll get 3/4 of pi out of that. Now, they're both valid, so that's good. Let's go k equals 2. Oh, that's interesting. This one's no good because that's out of range. It's right on the end point. Remember, we've got the round brackets here. Okay, so it's no good. This one that's okay. So that one's no good. Yeah. Now I think if we went k as 3, we'd be right out of business. But let's just check it out anyway. Right, 3 pi is no good, and 11 pi on 4. That's 2 3/4 pi. No good. Out of range. Okay. So that means we've captured everything, and we're confident. And what I usually do now, yes, I just put them all in a row from the most negative to the most positive in order. So therefore x is all of those things. All of those things, and thank you, Mr. Box. Let's keep going and smash another one. Okay, find the general solution to this thing, and hence find all the solutions to x in the interval from here to here. These are square brackets now, so those endpoints are included in the interval. Same procedure as before, guys. Hopefully you're getting a bit more used to them now. So let's go for it, okay? Do the general solution first. There it goes. I've just changed those terms in the brackets round so that the x is the first term, as I'm accustomed to looking at them in that form and feel more comfortable that way. That's fine. So let's just take that a step further. Therefore, tan of that would be 1 over root 3. Now, we'll do our basic angle trick now. The angle which has a tan of 1 over root 3 in quadrant 1 is pi on 6, guys. Pi on 6, okay? Let's do our cast diagram now and see which quadrants we're interested in. The ones in which tan is positive. There they are. I've put a circle around them, quadrant 1 and quadrant 3. And I've noted the angles in there from the horizontal. So that's a pi on 6 angle there. And this would be a, what would it be? 7 pi on 6, wouldn't it? But we don't have to worry about that with tan. We just do one of the angles and then say plus k pi, because the period of tan is just pi. But I'm getting a bit ahead of myself here. So we're saying that minus 3x plus pi on 6, the thing in the bracket here, right, is equal to pi on 6 plus k pi, right? If you wanted to, you could have said, okay, it's 7 pi on 6 plus k pi. That'll still capture every solution, because every progression of pi that you move through, you end up back here to the opposite diagonal situation in the opposite quadrant, okay? So by stepping through pi at a time, you just capture every single solution there is. Now what we've got to do is we've got to solve this for x. So let's subtract pi on 6 from both sides firstly. Yes. And we get that. Does that make sense? Yes, it does. It does. Now we're going to divide by -3. And therefore x will be that thing. How marvellous. And don't forget your k as an element of z, because you won't get full marks if you leave that out. Okay, you've got to specify it probably when you first introduce it, and I always like to put it in the answer just for good measure. Yep. Now that's our general solution. So now we've got to find the specific solutions which reside within this interval here. So I guess we should start with k as 0. Yes, excellent. Now we'll notch that up a bit now. Go for k as +1, see what we get. Oh yes, because this was negative, so if I'm moving upwards in the k, I get the negatives becoming more and more negative here. So that's good. That's within range, isn't it? Right, we better go with k as +2 now. Excellent, very good. Now what about k is +3? Oh, mighty fine. Now if we went any further than that, we'd be out of range, because that's right on the limit. Right, minus pi. So I think we can, oh there it goes, just to prove the point. That's out of range. Yep, yes, that is out of range. So therefore we've got all our ducks in a row now, expressing them from the most negative to the most positive. We can say that x is all of those things. And thank you, Mr. Box, you're a star. Yes, isn't this marvellous? We're going like an absolute steam train, right? One more question. I think we might as well have a go at number 5, don't you? Come on, we will. Find the general solution to this thing. Same old, same old. A little bit different in there, but no problem. And hence find all the solutions in that interval. Again, square brackets. So that's all right. Let's go with it. We've got 2 sine 4 pi x plus √3 is 0. Therefore, we'd say that sine of 4 pi x would be minus √3 on 2. Good. Now that the angle in quadrant 1, the basic angle in quadrant 1 that has a sine of √3 on 2 happens to be pi on 3. You need to know those really, really, really well. Those exact angle sine, cos and tan values. Yes. For pi on 6, pi on 3, pi on 4, 0, pi on 2, and all the other quadrant equivalents worked out from those. Okay, you need to know them. Yes, the basic angle in quadrant 1 is pi on 3. Let's draw our cast diagram, and looks like we're interested in those quadrants in which sine is negative. Okay, and I've drawn in the pi on 3s from the horizontal just to make absolutely sure that I know what I'm doing here. Now let's go with that then. Therefore we can say that 4 pi x, the thing in the sine brackets here behind the sin symbol, is equal to, now I'm using this fancy amazing high-tech intergalactic form of the solution here, so I'm saying it's n pi plus minus 1 to the n times the basic angle. Now I'm using the basic angle, you'll notice I'm using a negative basic angle to be very fancy and to prove to you that this works. So I'm using minus pi on 3, okay? I didn't call it 5 pi on 3, I called it minus pi on 3, and it will work just the same if you used minus pi on 3 or 5 pi on 3. It really wouldn't matter, guys. It really wouldn't matter. So now we're going to solve it for x, okay? That gets us our general solution, but I've been very devilishly cunning there. I've divided through every term by pi, divided both sides by pi. And what do I get? I get 4x equals n plus minus 1 to the n times minus a third. And then if I oh yes, oh gee, I shouldn't have, you can't forget that, guys. N is an element of z, okay? Yes. And therefore x, dividing both sides by 4, I get that. And Mr. Box, thank you, you're a star. Now, that's the general solution, guys, in the intergalactic kryptonite form, which Superman would approve of. And now we have to basically extract the solutions which reside within this interval, yes? So let's go for that. To find the solutions for that, yes, we will make n 0, and then we'll step it up and step it down from there and see where we end up. Make sure they're in range. Okay, if n is 0, now my goodness, let's work this out. Come on. That'll be nothing. Now, minus 1 to the 0 is 1. So it's just that, isn't it? Right, and that's in range. So that's good. Very good. Let's go up 1 until we get out of range, okay? N is 1. Now, what's that going to do? That's going to get 1/4 plus negative 1 times negative a 12th, which would be plus a 12th, wouldn't it? So it's 1/4 plus a 12th, isn't it? What is that? That's 3/12 plus 1/12, which is 4/12, which is a third. Excellent. Excellent job. That's still within range, isn't it? It is. Let's go with n equals 2. We're on a roll here. Oh, goodness. Now, hang on. What is that? How did we get that? That's 2 over 4 is a half, and that's minus 1 squared. Oh, yes. Okay, which just makes it plus 1. Plus 1 times negative a 12th is just that. So it's a half minus a 12th. That's 6/12 minus 1/12, which gets us 5/12, and we're still in range. My goodness, this is going well. Right, okay, n is 3 now. Okay, now we're getting in the rhythm of this. That's 3/4. That'll be negative 1 to the 3 is negative 1. So that'll be negative 1 times negative a 12th, which you'll get plus a 12th. So that looks like 9/12 plus a 12th is 10/12 or 5/6. Goodness gracious me. That's good, isn't it? Do you see how to do it? Good for you. If n is 4, you must get that. We'll just keep going now. Oh, that's still within range too. Goodness, when are we ever going to get out of range? I think that's about the limit. Yes, I think I did check that out. If you go n is 5, you're out of range, guys. So we're going backwards now. N is minus 1, okay? Now, if n is minus 1, that'll be minus 1/4 plus minus 1 to the minus 1. Well, that just means 1 over minus 1, which is still minus 1. So the upshot of it is you get minus 1 times minus a 12th, which is plus 1/12. So it's minus 1/4 plus a 12th. My goodness, I'm getting my head into a mess here. Minus 3/12 plus 1/12, which would be minus 2/12, which would be minus... what's that? Minus a 6th, isn't it? Yes, it is. Yes, there you go. So therefore, let's do the next one. N is minus 2. Now, apparently you get that, okay, which would be, what's that? Minus a half is minus 6/12 minus 12, minus 7/12, I think. Yes, good. We're still in range, guys. We can go all the way up to minus 1. Right, so let's do minus 3. That's supposed to be minus 3. Just a minute, I'll fix it. Right, fixed. So what did I say? So if n was minus 3, x would be minus 3/4 minus 1 times negative 1/12. And goodness me, my head is getting too sore to work that out. It's minus 2/3 apparently. Yeah, that's right. Minus 9/12 plus 1/12 is minus 8/12, which is minus 2/3. All right, we're still within range. Goodness, this is taking forever, isn't it? We better hurry up. Over the page, I think. There's one more to go, I think, before we get out of range. If n is minus 4, x is that. Ah, that's out of range. That's out of range. Oh, goodness. Finally, we got out of range. That's good. Now, that means we've got all the solutions now. So let's put them all in a row from the least to the highest, e.g. the most negative to the most positive. There they are. All the ducks are in a row. Quack, quack. And that's the end of the show. How did you like it? I hope you enjoyed it. That's how to do general solutions of trigonometric equations. Now, you redo that, more practice, and you'll be an absolute expert. Okay? Thanks for coming, and we'll see you soon.